Very good afternoon, everyone. I'm Dr. Vaibhav Pandit, and today we are going to discuss the topic titled Wavelet Transformation. Actually, this is the topic for our subject image processing. This subject is also known by DIP, digital image processing, along with the knowledge of computer vision, machine vision. If you require, these are all the fundamentals here. So basically, I have lot many videos for this particular subject already available on the online platform, and this is one of the session to solve with your doubts here. So in the previous session, I have addressed image pyramids. So that topic, image pyramids, and this the current topic, wavelet transformation, both are having the background of multi-resolution analysis, very important topic in the signal processing. Our image as a signal, so it is a two-dimensional signal. Image is of course a signal here, so this is really very important here. And image pyramids, the fundamentals we have already discussed upon. So let us have one sample problem based on to the wavelet transformation to practice for. So let us have the problem statement. So this problem statement is holding three parts to find the solution for. In the first part, we have the statement as if the input to the three scale FWT filter bank is the Haar scaling function denoted by phi of n is equal to 1 for the values of n from 0 to 7 and 0 elsewhere. The question is, what is the resulting transform with respect to Haar wavelets? The second part is denoted by part B. The question is, what is the transform if the input is the corresponding Haar wavelet function denoted by psi as a function of n, holding the values, the 8 values are there in this set, the first 4 values are equal to 1 and the rest of the remaining 4 are denoted by minus 1 for n is equal to 0 to 7 here. So this is what the second part here, and the last part it is, what input sequence produces transform, that is already provided in the statement. So we have the first 6 samples of the transform to be equal to 0. The seventh one is equal to capital B, and the last it is denoted by 0. So this is with the non-zero coefficient denoted capital W suffix I as a function of 2 comma 2, that is equal to capital B here. So part A, B and C constitutes our problem statement we are going to consider as a practice for wavelet transformation. Now if you see the first part here, so in this first part we are having the abbreviation FWT. So the question is, if the condition is first of all made here, if the input to the 3 scale FWT, so FWT stands for the fast wavelet transformation here, and with the help of the fast wavelet transformation, there it is a consideration of the filter bank here, and the filter bank is of the 3 scale here. So before solving the exact question, you should have a knowledge of what exactly the fast wavelet transformation is. With the help of this transformation tool, what is that filter bank and what level, that means here it is the 3 scale filter bank. So it should be first of all known to you people. Along with there it is a mention of Haar scaling function here. So see here, Haar transformation is the basic and the first one wavelet transformation. So for that I have a lot of videos available on the online platform with Ekeeda here. So now Haar function. There are two types of the Haar functions here. The first one is the mention of the scaling function, and if you see the part B here, there it is a mention of Haar wavelet function, that is denoted by psi as a function of n here. So while solving these parts A, B and C, we shall have the knowledge of the wavelet transformation. All the fundamentals I will try to cover in this 1 hour live session here. So first of all I will introduce you the filter bank structure that is expected to have the scaling function with the given values. The given value is 1 for the every sample. The index is, it is denoted for small n from 0, 1, 2, 3, 4 and so on up to maximum 7 here. Elsewhere we have the value is equal to 0 here. So let us have first of all the visualization of the 3-scale FWT filter bank here. So here it is. Now you see the function represented here. This is basically the one-dimensional function under consideration, and the functional domain in general here it is denoted capital V suffix capital J here. And with the help of this filter banking here, as we have the two types, analysis filter bank and that of the synthesis filter bank, here it is the analysis type here. So we have the functional spaces denoted at the different stages here. We have capital W suffix J minus 1, capital W suffix J minus 2 here. We have V suffix J minus 1, V suffix J minus 2, W suffix J minus 3, V suffix J minus 3. So if we only visualize the hierarchy with respect to the functional spaces here, so we have this sequence. At the top we have, as denoted in the earlier diagram also, we have V suffix J. Then we have the two parts, V suffix J minus 1 and W suffix J minus 1. V suffix J minus 1 is having again the two parts leading to V suffix J minus 2, W suffix J minus 2. Further we have the bifurcation into the two roots. We have V suffix J minus 3 and W suffix J minus 3 here. So coming back to the question. The question in part is, if the input to such a 3-scale fast wavelet transformation filter bank is the Haar scaling function denoted by psi as a function of n holding the value 1 for all the 8 elements here, what is the resulting transform with respect to the Haar wavelet? Here it is the simple question here. So only the condition is that we are providing the input of the scaling function for the Haar type here, having all the elements equal to 1 here. So where we are applying the input, that should be known to you people. That is why I have clarified with the help of the two illustrations here. So I hope the thing is clear. So let us find out the answer for this part A question here. So here we can denote the input with the help of the phi of n equal to the 8 elements in this set, all having the value 1 here. So we can also denote it by phi suffix 0 comma 0 as a function of n for a 3-scale wavelet transform with the Haar scaling and the wavelet functions here. Now since the wavelet transform coefficients are measuring the similarity of the input to the basis functions, the resulting transformation we can denote like this. So here we denote in a set the first element as W suffix phi as a function of 0 comma 0, the second element W suffix psi as a function of 0 comma 0, then W suffix psi 1 comma 0, W suffix psi 1 comma 1, W suffix psi 2 comma 0, further W suffix psi 2 comma 1, then W suffix psi 2 comma 2, and lastly W suffix psi 2 comma 3. So if we represent the values, the first value will be 2 under root 2 and all the rest of the values will be equal to 0 here. Now you see here the first representation that we have W suffix phi as a function of 0 comma 0. It can be computed while having the substitutions J0 is equal to K, both to be equal to zeros here. So this can be the solution to part A here. Now recall back the part B question here. In the part B, the question is, what is the transform if the input is the corresponding Haar wavelet function? The wavelet function is already provided in the problem statement, that it is psi as a function of n. Here the first 4 elements are equal to 1 and the last 4 elements are denoted by the values minus 1. So here it is the index variable to denote the 8 elements n from 0, 1, 2, 3, 4, 5, 6 and 7 here. So this is what the question here. So for this question also we can use the same reasoning that we have utilized to find the solution to the part A here. So simply we can write down the answer here. The answer will be the 8 elements here we have represented here. The first element will be 0. The second variable here, it will be 2 under root 2, and rest of the 6 elements are holding the values 0 here. Now, after finding solutions to the part A and part B here, we are going to solve the part C of the problem statement here. In the problem statement, we have the question: what input sequence produces the transform? The transform there it is provided. The first six elements are in 0, the seventh one is capital B, and the last one is equal to 0 with the non-zero coefficients denoted by W suffix I. In the bracket we have 2 comma 2, that is equal to capital B here. So now the answer to this part of the question can be given this way. So very first of all, for the given transformation we have the notation. The notation just now I have recalled: W suffix I in the bracket 2 comma 2, that is denoted by capital B in the question here, and all the other coefficients are denoted by the value 0 here. Now with this information, the input must be proportional to the function denoted here psi suffix 2 comma 2 as a function of small x here. Now the input sequence therefore must be holding the form where the first four elements are equal to 0, the fifth one is equal to positive c, then next one is minus c, and rest of the two are equal to 0. Now at this point we don't know the value of the c here. Now in order to determine what exactly the c is there, so that we can put it into the earlier representation, the positive c and the negation of the same here, we utilize the mathematical expression that is denoted W suffix I as a function of j comma k, that is equal to 1 upon under root m, the summation operation over the product of f of x with the wavelet function here psi suffix j comma k as a function of x here. The summation is for the variable x here. Now in this equation, if we have w suffix psi as a function of 2 comma 2, so here we obtain the 8 terms as denoted 1 upon under root 8. In the set we have f of 0 multiplied to psi suffix 2 comma 2 as a function of 0, the first term, added by f of 1 with the multiplication to the psi suffix 2 comma 2 as a function of 1. In the similar way we have f of 2 into psi suffix 2 comma 2 as a function of 2, f of 3 into psi suffix 2 comma 2 as a function of 3. So f of 4 psi of 4, f of 5 psi of 5, f of 6 psi of 6, f of 7 psi of 7. So this way the 8 combinations here are there in the relevant 8 terms inside the bracket, that is all multiplied by 1 upon under root 8 here. Now the simplification here we can make in the next step by substituting the values here. Here we get 1 upon under root 8 multiplied to the product of 0 added by again the product of zeros, then again the multiplication of zeros for the 2 times here, then we have the product of c with that of 2 here, then minus c with that of minus 2 here, and again the 2 times we have the multiplications of zeros here. So this will lead us to the value of w suffix I as a function of 2 comma 2 to be equal to 1 upon under root 8, the addition of twice c with again twice c here. So this becomes 4c divided by under root 8, which we can simplify to represent as under root 2 times c here. So w suffix I as a function of 2 comma 2 is nothing but under root 2 times c here. So because of this particular coefficient is known to be having the value as represented in the problem statement by capital B here, here we have the relation to denote as under root 2 times c is equal to capital B. In another way also we can denote it as c on the left hand side. So in terms of capital B we shall write c is equal to under root 2 divided by 2 times capital B here. So therefore the input sequence we can judge. So in place of C we can substitute the RHS of this particular equation, and the input sequence here we denote it as the first 4 elements are equal to zeros, then under root 2 times capital B divided by 2, followed by we have negation of the same, that is minus under root 2 times capital B divided by 2, and the last two elements are equal to 0 here. So now in order to check the result, substitute these values into the equation. The equation we have already denoted here. So we have w suffix I as a function of j comma k is equal to 1 upon under root m, the summation x for the product of f of x into the psi as a function of x, where the suffix are with the notations of the parameters denoted j comma k here. So therefore we get w suffix I as a function of 2 comma 2 with the help of the equation. Here we have 1 upon under root 8 multiplied to the set of the values, where we have the 8 values added to each other, 0 plus 0 plus 0 plus 0. Then we have under root 2 by 2 capital B by 2 here, and the negation of the same is also added, and finally we have the rest of the two zeros here. So we get it to the form 1 upon under root 8 into root 2b added to root 2b here. So this is absolutely equal to capital B here. So this way we have the solution to part A, B and part C of the problem statement under consideration here. See here, in this problem statement there it was consideration of the filter bank form with the help of the fast wavelet transformation here. So most of the times when the students are coming from the background of signal processing with the tools utilized till date, that is basically the popular one Fourier transformation here, the wavelet transformation is having certain advantages, that is why it is nowadays more popular than that of the Fourier transformation here. So you should be very much clear with your understanding what is there in the Fourier transformation and what we can have in the wavelet transformation there. In my earlier lectures also I have discussed these of the points here. So if you are not getting the things that I have performed to find out the solution in this current problem statement, let us have a recap of what the wavelet transformation is there as we switch from the Fourier transformation. And of course this will have a little bit modification as we have different types of the signals. Basically in the background of the signal processing we have the one dimensional signal, most time the used one here, and here in our subject as it is image processing, here image is a two-dimensional signal here. So we can have the wavelet transformation in one dimension, wavelet transformation in two dimensions as well here, and the FWT that we have dealt with, that it is the fast wavelet transformation. So it is basically the efficient way of implementation here, so that is why we are getting the fast results here. So basic transformation is the same, wavelet transformation here, just to speed up the computations and further implementation, there it is the tool, and of course it is popular while the practical use of the tool here. Now let us start with the wavelet transformation in the case of one dimensional signal here. So if we closely see the wavelet transformation here, we can have the three basic types that are really very similar to each other. They have the basic relationship with them as well here. So we first of all undergo through the generalized wavelet series expansion here. Then next to that we have the discrete wavelet transformation, that is really very popular here, and along with we should also have knowledge of the continuous wavelet transformation. So basically in this digital world the practice of the continuous wavelet transformation is really very rare, I can say here. It is of course the use of the discrete terms. So discretization, as it has been from the continuous domain representation of the signal information here. So you should have the knowledge of this one as well here. Now as we relate all these particular transformations of the wavelet domain here to what we have done with respect to the frequency domain exactly by the Fourier tools here, the counterparts of these wavelet transformations in the Fourier domain we can give one by one. For the first one, there it was the Fourier series expansion. I hope we are all well familiar with, and we have practiced the Fourier series a lot with the periodic signals. Now, after the Fourier series expansion, we have also learned the discrete Fourier transformation here. So, discrete wavelet transformation here we have as a substitute to the discrete Fourier transformation here. And for the continuous type of the wavelet transformation, we have the counterpart, that it is the integral Fourier transform here. Now, as like we have the fast Fourier transformation FFT, the very popular while applying the Fourier transformation to the discrete signals here. So, in the similar way, we have the fast wavelet transformation here. So, I hope the enough introduction I have given to the fast wavelet transformation. If the time permits, I will also go into the details of the same here. So these particular the wavelet transformations are basically supporting to have the definition of the computationally efficient implementation of the discrete wavelet transform, as just now I have discussed, that it is the fast wavelet transformation here. So one by one we shall go. We shall first of all address the wavelet series expansion, then the discrete wavelet transform along with the continuous wavelet transformation, and that too all for the one dimensional signal here. Then we can switch to the two-dimensional signal, our image signal here, because it is quite convenient to first of all deal with only one dimension. When there are two dimensions, of course the complexity increases here. So only the linear modifications we have to carry forward if you have the strong concepts while working with the one dimensional signal here. So let us address first of all what exactly the wavelet series expansion look like. We shall deal with the mathematical expression for that particular representation here. So here for wavelet series expansion, we begin by the definition of the wavelet series expansion for the function that usually we denote f of x. So this is belonging to the domain represented L square as a function of capital R, and this is relative to the wavelet function denoted by psi of x and the another scaling function phi of x here. So one point you should note that while working into the Fourier transformation, we have only one function to be operating on, whereas in the wavelet domain we have the two functions here. One is the scaling function and another is the wavelet function here. Both the functions are characterized by the different features and both are helpful for the implementation and the strong mathematical foundation of the wavelet theory here. Now, for the wavelet series expansion of the one-dimensional signal, we can give the mathematical expression as f of x in terms of the two terms here. The first term, it is expressed with the help of the summation with the index variable small k, that is operated over the c of k in the suffix we have j0 multiplied to the scaling function phi of x in the suffix we have j0 comma k here. So this is all added to the double summation. For the first summation, we have the index variable j ranging from j0 to infinity. The second summation, as in the earlier term, we have for the index variable k, and this is all operating over the product of d of k in the suffix j in multiplication to psi of x in the suffix j comma k here. So this is what the simplest representation of the wavelet series expansion. For your clarification, you can also outline this particular expression and understand it. It is really very simple to understand. So in this representation, we have J0 is basically an arbitrary starting scale here from where we begin. Now here in this representation, we have the two types of the coefficients here. The first one is the approximation, also known by the scaling coefficients, and that it was represented in the earlier expression. Let us denote that earlier equation by equation number 1 here. So here this scaling coefficient or the approximation type of the coefficient, that is denoted c of k in the suffix j0 here. So this is basically the integral of the product f of x into we have the scaling function pi as a function of x. In the suffix we have j0 comma k, and along with this integral notation we have the differential denoted dx here. Now, after this approximation or scaling type of the coefficient, the another type of the coefficients here we have, these are also known by the name detail coefficients or the wavelet coefficients here. So they are denoted by d of k here. In the suffix we have j here, and this is of course the integral of f of x with the wavelet function here. See, for determining the scaling coefficients we have the integration of the signal with the scaling function here. So for the wavelet coefficients we have the integral of the signal with the help of the wavelet function here. So the wavelet function here we have psi as a function of x. In the suffix we have j comma k here. The integral sign is there along with the differential denoted dx here. So now if you recall back the earlier equation whereupon the use of both of these equations, the approximation and the details, or in another words you can call scaling coefficients and wavelet coefficients, is made thereupon. So you will come to see that the first term on the right hand side of the equation is using the scaling function to provide an approximation of the input function. See, the input function is one dimensional signal as denoted f of x at the scale level denoted j0 here. Now here, for each of the higher scales that are greater than the j0, for the second term, a finer resolution function, that is a sum of wavelets, is added to the approximation to provide the increasing details here. See here, the motive to work with this particular tool is to extract more and more information here at the different stages here, and that it is the most popular feature of what we call MRA, the multi-resolution analysis theory, for which these are the various tools here. Image pyramids, our previous topic in the last session, was also belonging to the multi-resolution analysis here. Now here, coming back to the track here, if the expansion functions form an orthonormal basis or a tight frame, which is often the case, the expansion coefficients are calculated by the two equations that just now we have discussed on the earlier slide here. So if the expansion functions are part of the bi-orthogonal basis, here we have the denotions by phi and the psi here in these particular equations correspondingly for denoting the scaling and that of the wavelet here, they must be replaced by their dual functions respectively. Now here we are going to visualize one illustration. In this illustration we are having a wavelet series expansion made for the one-dimensional function as denoted y is equal to x square here using the Haar wavelets. So here we see the illustration. We have the total 6 parts here. In the first part you see the basic relation y is equal to x square here. So y has been plotted onto the vertical axis, whereas we have the x onto the horizontal axis, and as the relation y is equal to x square goes on, we start at 0 here. Here it is 0 for the y axis, y parameter, and here it is the 0 for the x parameter. The relation is graphically plotted here with the help of the parabola. Here we have the relation plotted here. Now the functional spaces here we can denote. For example, in the part B we have V0, then in the part C we have W0, we have V1, we have W1, we have V2 also here. So this is all there has been represented with the help of the Haar wavelets here. The Haar wavelet is the basic wavelet here. So in the Haar wavelet, either we have the positive amplitude or the negative amplitude, and both the amplitude levels in the positive and negative are at the constant levels, and this is of course for half duration here. So here we go for the expansions of the coefficients given by the mathematical representations. Here we can have the values for the different coefficients, both for the scaling as well as for the Wavelet coefficient here. So for the scaling coefficient, here we have c suffix 0 as a function of 0 that has been computed here. The integral 0 to 1 over x square. X square, here it is the substitution of the functional representation. We initially had f of x here. So this is our function here. So this is our signal, and that it is operated with the help of the scaling function as represented phi suffix 0 comma 0 as a function of x. Here it is the scaling function, whereas the psi functions in the next three expressions are the wavelet functions here. So for the scaling coefficient, we have the integral operation over the function with the help of the scaling function. The integration will lead to the simplified form integral 0 to 1 over x square dx here. So this will of course be x3 divided by 3. The limits we apply from 0 to 1, we get the value of the scaling coefficient is equal to 1 divided by 3 here. Now in the similar fashion, for determining the values of the wavelet coefficients, d suffix 0 of 0, d suffix 1 of 1, 0, d suffix 1 of 1 also. So here we go for d suffix 0 of 0, we have the integral from 0 to 1. The x square, it is operated by this particular function, and here we have the split of the limits from 0 to 0.5 and then 0.5 to that of the 1. We obtain finally for the wavelet function here, we obtain the first coefficients as denoted minus 1 by 4 here. Now next to that, d1 of 0 we obtain minus of under root 2 divided by 32, whereas d1 of 1 is equal to minus of 3 under root 2 divided by 32 here. So here we get the wavelet series expansion for the function denoted by small y here. So small y we express with the various functional spaces represented. So mathematically we can denote it as y is equal to the first coefficient we are representing in this mathematical expression here, 1 by 3 multiplied to the scaling function phi suffix 0 comma 0 as a function of x here. This is what the functional space denoted v0 here. So this is further added to the another coefficient. Here it is the wavelet coefficient that we have just now determined, minus 1 divided by 4 multiplied to the wavelet function. Here we have psi in the suffix 0 comma 0. This is all as a function of x here. So this is nothing but the representation of the functional space w suffix 0 here. The combination of the two, that it is v0 with that of the w0, is nothing but the functional space denoted v1 here. So this combined functional space v1 is further added by the square bracket where we have minus of under root 2 by 32, another the wavelet coefficient, multiplied by the wavelet function. Here we have psi suffix 1 comma 0 as a function of x here, minus we have 3 under root 2 divided by 32 in multiplication to the wavelet function psi as a function of 1 comma 1 as a function of x here. So this is nothing but the functional space w1. So this series expansion will be going on as it is here. So here we can simply denote the v2 function space, the consideration of both of the v1 and that of the w1 as in the previous step here. So this is equal to basically the v0 functional space along with the w0 and finally with that of the w1 functional space here. So the close relations of the wavelet representations here, we had the three choices here. The first, that it was for the series expansion with this mathematical tool here, that I think this much of information is enough to clarify the things associated with this particular tool here. Now the next one is really very popular, and that it is known by DWT. So DWT abbreviation stands for the discrete wavelet transformation here. So as you call DWT, it is really very similar to what you have been working with. Here, there it was the discrete Fourier transformation, that it was DFT here. So as you compare, like the Fourier series expansion, the wavelet series expansion that just now we have seen, that maps a function of the continuous variable into a sequence of coefficients, and the same thing can be carried forward from DFT to that of the DWT here. So if the function that is being expanded is a sequence of the numbers like the samples of the continuous function, the function that we have denoted f of x, the resulting coefficients are called the discrete wavelet transformation as denoted by DWT of the original function denoted f of x here. Now the series expansion that just now we have defined here, that will be now be recalled as the discrete wavelet transformation pair. This pair is of course for the pair of the scaling as well as that of the wavelet functions here. The two mathematical expressions certainly I will show you here. The first one here, it is denoted w suffix, the scaling function notation is by pi here. So in the bracket here we have j0 comma k. So this is expressed as 1 upon under root m multiplied to the summation operation of f of x with that of the scaling function psi phi as a function of x here. In the suffix we have j0 comma k here, and x is of course the variable for the summation to carry on. Now the second notation is for the function denoted w suffix psi here. So psi is for denoting the wavelet function here. In the bracket here we have j comma k here, and this is equal to 1 upon under root m in multiplication to the summation carried on to the product of the signal f of x with that of the wavelet function, that it is psi as a function of x. In the suffix we have j comma k here. So here it is for j that is greater than or equal to j0 here. Now the generalized representation of the original signal, we have been representing by f of x, as here it is on the left hand side here. So this is in terms of the 2 as added on the right hand side here. So in the first term here we have 1 upon under root m, the summation operation over the w suffix pi in the bracket j0 comma k multiplied to the scaling function phi as a function of x in the suffix j0 comma k here. So this is the first term, and the second term you see 1 upon under root m, we have the double summation here. The first summation is for j is equal to j0 to infinity. The second summation is operated for the index variable k, and this is for the product of, we have w suffix psi as a function of j comma k multiplied to that of the wavelet function psi in the suffix j comma k as a function of x here. So for the Haar wavelets, the discretization of the scaling and the wavelet functions is employed here, and that has been there in use for the transformation. So for the transformation we require the basis functions. So either you call them the transform functions or the basis function, it is one and the same. So based on the basis function only we can have the another type of the representation of the same kind, and that can be with the convenient interpretation here. So this is corresponding to the rows, and that is for the Haar transformation matrix, the order we can denote it as m by m here. Now the coefficients defined are here usually called upon as the approximation or the scaling coefficient, and the second type is that detail coefficients, also known by the wavelet coefficients here. So these are the points to be noted here. Now hereupon we have utilized the integral functions in the series expansion that have been replaced by the summations in the current representation, as we have switched from the series expansion to that of the discrete domain wavelet transformation here. And one more change has occurred, that the normalization factor that it was represented 1 upon under root 2, the reminiscent of the DFT has been added to both of the forward and inverse expressions here, and this factor could have alternatively be incorporated into the forward or inverse alone as 1 upon m as well here. So now whatever the equations we have shown here are really valid and true for the orthonormal basis and the tight frames alone here. For the bi-orthogonal basis, the terms must be replaced by their duals here. So these are the very important points here. See, whenever you are putting forward any new transformation tool that is beneficial for the signal processing task here, it should be always following the orthogonality and orthonormality conditions here. So the orthonormality and orthogonality conditions are also valid true with the help of the scaling function and that of the wavelet function that we have discussed here. Now, after a discussion on the wavelet series expansion, then the use of the discrete domain wavelet transformation, we should also have a brief review of the continuous domain wavelet transformation here. So we have the continuous wavelet transformation here. So as we are dealing with right now with the discrete domain here, so the continuous wavelet transformation is basically the natural extension of what we have been dealing, that it is discrete wavelet transformation, and here the notation for the continuous wavelet transformation is the abbreviation we can use, that it is CWT. So CWT for the continuous wavelet transformation and DWT is for the discrete wavelet transformation. So here the CWT will transform a continuous type of the function into a highly redundant function of the two continuous variables. Those are the translation and the scaling here. See, these are the two operations, the translation and scaling, and these are also operated along with the use of the scaling function and that of the wavelet function here. So the continuous function will be fed as input to that of the CWT, continuous wavelet transformation, whereas of course the input is of the discrete type when we are going to work with the help of the DWT, the discrete wavelet transformation here. Now you see, with the continuous wavelet transformation, the resulting transform is really very easy to interpret and valuable for the time frequency analysis here. One point you should note that the Fourier transformation is lacking the time information, it is only providing the frequency analysis here. So that is why sometimes the frequency domain we also refer by the name Fourier domain here, whereas in the wavelet domain we have certain added information of the temporal in type also, that is with respect to the time component here. Now the continuous wavelet transformation we are discussing, so this is for the continuous and square integrable function, the usual notation f of x, that is relative to a real valued function, the wavelet function psi of x here. Mathematically it will be described as, we have capital W suffix psi as a function of s comma tau here. So it is the integral from minus infinity to infinity for the product of f of x with psi as a function of x, in the suffix we have s comma tau, and dx the differential here. So in this particular representation, the function that you see on the right hand side, that it is psi in the suffix s comma tau as a function of x here. So this is equal to 1 upon under root s in multiplication to the psi as a function of x minus tau divided by s here. So in this particular notation for the continuous type of the wavelet transformation, here it is the new entry of the two variables s and tau. These are called the scale and the translation parameters in respective manner here. Now given the transform, if the transform is provided for the function f of x, that can be obtained using the inverse continuous wavelet transformation also. So the reversal of the forward, that we are known by the inverse transformation here. So if simply we refer to that of the CWT, it will be of course the forward continuous wavelet transformation, and if we refer to that of the ICWT, it will be the inverse continuous type of the wavelet transformation here. So here we have the expression of f of x is equal to 1 upon capital C suffix psi, the two integrals, the first one from 0 to infinity and the second one from minus infinity to infinity, correspondingly for d tau and ds here, is there for the multiplication of w suffix psi as a function of s comma tau with that of the psi as a function of x in the suffix s comma tau divided by s square here. So here in this representation, we see before the integral there it is the normalization by the factor c suffix psi here. So c suffix psi is the Fourier transformation of the wavelet function, that it is denoted by psi as a function of x here. So c in the suffix psi is equal to the integral the mod square of psi of u divided by mod u into du here. So now after this much of information with first of all the series expansion, then that of the discrete type of the wavelet transformation, and now here the continuous type of the wavelet transformation here, we shall like to conclude the topic for the one dimensional case here. So before conclusion, I will like to have a brief illustration here that is giving us the idea of the continuous wavelet transform. Here we are having the four parts to the illustration here. So the continuous wavelet transformation is shown into the part C and part D here, and the corresponding Fourier spectrum in the part B for the one dimensional function as represented in the part A here. So here it is the part A, the one dimensional signal as usually we have been denoting by f of x here, the corresponding Fourier spectrum as the corresponding function is fed as input to the Fourier tool here, we obtain the spectrum here. Whereas in the part C and in the part D we have the continuous wavelet transformation here. So here we have the s parameter, the tau parameter as just now we have discussed for the representation of the transformation as w suffix psi as a function of s comma tau here. So here also we have the representation in the two dimension. Here it is the two dimensional representation of the function, whereas the three dimensional representation of the function is there. Now we shall highlight few of the things with respect to the very popular FWT, the past implementation of the wavelet tool here. In the problem statement that we have dealt in the beginning, there also it was a mention of the past wavelet transformation, and based on this FWT there it was the use of the filter bank of the analysis type here. So we can call it FWT, the abbreviation for the past wavelet transformation, which is a computationally efficient implementation of the DWT that just now we have seen here. So this is making use of a very interesting and surprising but fortunate relationship between the coefficients of the DWT at the adjacent scales here. So that is why the efficiency leads it to give the name by the fast wavelet transformation here. So this is basically called as the Mallard's herringbone algorithm here. The name of the inventor here, Mallard here, and it was there in the year 1987 around here. So we also have a topic that is describe origins of the wavelet, the complete history. You can see how the wavelet theory has been evolved in the past few decades here. Now the FWT here, the fast wavelet transformation, basically is very resembling to the two band subband coding scheme here. So now here for example we consider the multi-resolution refinement equation, that it is denoted by the notation phi as a function of x, that is equal to the summation over the variable n here for the product h suffix phi of n here in multiplication to under root 2 times the scaling function phi as a function of twice x minus n here. So now if we have scaling of the independent parameter x by the label 2 to the power j, translating it further by the value k and letting small m is equal to twice k plus n, it will give us, we have phi as a function of 2 to the power jx minus k is equal to the summation for the variable n, or the multiplication h phi as a function of n multiplied to under root 2 times phi in multiplication to the bracket that has twice of the bracket 2j 2 to the power j into x minus k minus n here after bracket completion here. Now the next representation also we can give it for the same, that is the summation by the variable m for the h phi of m minus twice k multiplied to under root 2 times phi as a function of 2 to the power j plus 1 times x minus m here. So here the scaling vector, here we can denote in the previous expression as it is used h suffix phi here. It can be thought of as the weight that is utilized for the representation of the expansion function here, and it has the analogous result that can be obtained for the wavelet function here. So let us have the consideration of the equations that define the discrete wavelet transformation here. So here we have the two equations here. The first one with the help of the scaling notation and another one that is with the wavelet notation. For the scaling notation we have w suffix phi in the bracket j0 comma k, that is expressed in terms of 1 upon under root 2 times the summation for the index variable x for the product of f of x with that of the scaling function. Here we have phi as a function of x, in the suffix we have j0 comma k here. The second function is for the wavelet function. We have the notation w suffix I in the bracket j comma k here. So that is equal to 1 upon under root m, the summation with the index variable x here, that is for the multiplication of f of x with the psi of x here, in the suffix we have j comma k here. Now if we have substitution of the wavelet definition equation, that it is the psi of x in the suffix j comma k is equal to 2 to the power j by 2 psi in the bracket we have 2 to the power j into x minus k here. So that time we obtain w suffix psi in the bracket j comma k, that is equal to 1 upon under root m in multiplication to the summation for the variable x here, where we have f of x multiplied to 2 to the power j by 2 in multiplication to psi as a function of 2 to the power j into x minus k here. So that time we can express, we have w suffix psi as a function of j comma k expressed as 1 upon under root m the summation x for f of x into 2 to the power j by 2 in multiplication to the square bracket that again has a summation for the index variable m over the vector h suffix psi as a function of m minus twice k multiplied to under root 2 times the scaling function psi as a function of 2 to the power j plus 1 times x minus m here. So if we have the interchanging of the summation and the integration and then the rearrangement if we made, so that time we can have the modified representation given as w suffix psi as a function of j comma k, it is equal to, we have the summation with the index variable m for h suffix psi in the bracket m minus 2k in multiplication to the square bracket that has 1 upon under root m in multiplication to the summation with the index variable x for f of x into 2 to the power j plus 1 divided by 2 into the scaling function phi in the bracket we have 2 to the power j plus 1 x minus m here. So therefore we can have the representation in the simplified form, that it is w suffix psi in the bracket j comma k in terms of the summation with the index variable m for multiplication of the vector h suffix psi in the bracket m minus twice k with that of the w suffix psi phi in the bracket j plus 1 comma m here. So this was all we can represent up till now here. Now the discrete wavelet transformation wavelet coefficients, also known by the detail coefficients at the scale level denoted small j, are basically the functions of the discrete wavelet transformation scaling coefficients, also known by the approximation coefficients at the scale j plus 1 here, and therefore we have the relation denoted that it is w suffix phi as a function of j comma k is equal to the summation that it is s suffix phi in the bracket m minus 2k into w suffix phi in the bracket j plus 1 comma m. So when we observe the two equations along with this one, so we reveal that a remarkable relationship between the dwt coefficients of the adjacent scales is there here. So both the notations in these representations here, we have w suffix phi of j comma k and w suffix psi of j comma a k here. The scale j approximation and the detail coefficients. See, the approximation is also known by the scaling information. The detail coefficients are also known by the wavelet coefficients here. So these can be computed by having the perform of the convolution operation. So convolving w suffix phi of j plus 1 comma k, the scale j plus 1 approximation coefficients with the time reverse scaling and the wavelet vectors respectively denoted by h suffix phi of minus n and h suffix psi of minus n, and further subsampling the results, we obtain the relationship here. Now let us have the visualization of one figure that reduces the operations, and that is of course shown with the block schematic format here, and here it is identical to the analysis portion of the two band subband coding and decoding system here. So here we visualize the fast wavelet transformation analysis bank here. So here it is one step here. So you see here at the start we have w suffix phi as a function of j plus 1 comma n here, and we have the two branches leading to w suffix psi of j comma n and w suffix phi of j comma n. In the respective paths we have the vectors denoted h suffix psi of minus n, h suffix phi of minus m. In along with we have the downsamplers by the factor 2 here. So for the analysis filter bank we always have a function split it into multiple representations here, whereas in the synthesis filter bank we have the multiple representations combined to a composite representation here. So for the analysis type, from left hand side we have to go for multiple paths here, and reverse is the case if we go for the synthesis filter bank here. So the relationship of the corresponding thing that we have in this particular block schematic with the subband coding we have already discussed here. So therefore we can mathematically write it as we have w suffix psi in the bracket j comma k is equal to, we have h suffix psi of minus n convolved with w suffix phi of j plus 1 comma n, provided n is equal to twice k and this k is always greater than or equal to 0. Along with we have another relation, that is again with the help of the convolution operation, where we have w suffix phi as a function of j comma k, it is equal to h of phi as a function of minus n convolved with w suffix phi as a function of j plus 1 comma n here, provided n is equal to twice k and k is always greater than or equal to 0 here. Now where the convolutions we have to evaluate at the instances n is equal to twice k and for k greater than or equal to 0, as already represented on the right extreme here. Now evaluating both of these convolution operations at the non-negative and the even indices is equivalent to filtering and downsampling by the factor 2 that it was represented in the earlier schematic here. Now, in order to compute the development of the fast wavelet transformation, the filter bank in the previous figure can be iterated to create the multi-stage structures for computing the discrete wavelet transform coefficients at the two or more successive scales here. So let us have the example with the help of the next figure that shows the two-stage filter bank for generating the coefficients at the two highest scales of the transformations here. So let us visualize it, a two-stage or the two-scale FWT analysis bank. In the problem that we addressed at the beginning, that it was a three-scale fast wavelet transformation analysis bank here. So here we visualize the analysis bank with only two scales here. So only two times the branching is made, as we started from the representation of this function from the left extrema here. So here we have f of n for the functional space denoted w suffix phi in the bracket j comma n here. So we have the branching further, we obtain w suffix psi in the bracket j minus 1 comma n here for the first path here. The second path is again bifurcated and leads us with w suffix psi in the bracket j minus 2 comma n. Next to that we have w suffix phi in the bracket we have j minus 2 comma n here. So here the first filter bank will split the original function into the low pass, the approximation component, and that correspond to the scaling coefficients as denoted. We have w suffix phi in the bracket j minus 1 comma n, and a high pass, the detail component and the corresponding to the coefficients denoted w suffix psi in the bracket j minus 1 comma n here. So the graphical illustration of the same we can also have that we show here. So the frequency splitting characteristics, we show it like this. So on the horizontal scale we see a frequency as the independent parameter denoted by omega in terms of the angular values here, whereas on the vertical axis we have the magnitude denoted or the mod of h as a function of omega here. So now here it is the case where the functional spaces, as just now we have discussed, v suffix j minus 1, v suffix j minus 2, w suffix j minus 2, w suffix j minus 1, all we have discussed here. The frequency markings you see for the pi by 4, pi by 2 and that of the pi here. So the scaling space v suffix j is split into the wavelet spaces w suffix j minus 1 and the scaling subspace v suffix j minus 1 here. The spectrum of the original function is split into the two half band components here. The second filter bank here, as like the earlier figure, splits the spectrum and the subspace v suffix j minus 1, the lower half band, into the quarter band subspaces as denoted w suffix j minus 2 and v suffix j minus 2, with corresponding to the discrete wavelet transform coefficients denoted w suffix psi of j minus 1 comma n, and for the scaling the corresponding notation w suffix phi of j minus 1 comma n in the respective manner here. Now here in the block schematic we have visualized the two-stage filter bank that is easily extendable to any number of the scales here. Now the third bank, for example, if there it would be, so it will operate on the w suffix phi as a function of j minus 2 comma n coefficients here. The highest scale, that is j minus 1 coefficients, are computed first of all, and the lowest scale, that is j minus capital P, will be having the last priority here. So if the general function as denoted f of x is sampled above the Nyquist rate, its samples are good approximations of the scaling coefficients at the sampling resolution and can be used as the starting high resolution scaling coefficient inputs here. So let us for example have the consideration of a brief example, that is a discrete function here denoted f of n is equal to the four coefficient values here. 1 comma 4 comma minus 3 comma 0 here. So here we have the corresponding vectors h suffix phi of n, opting the value 1 upon under root 2 for n is equal to 0 1. Elsewhere we have the value to the vector is equal to 0. For the wavelet case we have h suffix psi of n, opting the value 1 by root 2 for n is equal to 0. Its negation for n is equal to 1. Elsewhere again the 0 here. So these are the corresponding two functions that are used to build the fast wavelet transformation filter banks, and they provide the filter coefficients in the corresponding manner here. So again we have visualization of one more figure that shows the sequences that result from the required fast wavelet transform convolutions and the further downsamplings here. The function under consideration f of n itself is the scaling or the approximation input to the leftmost filter bank here. So here we have the illustration showing the computation of a two-scale fast wavelet transform of the sequence as considered. You see here that it is f of n is equal to 1 comma 4 comma minus 3 comma 0 here, and that is of course with the use of the most simplest wavelet tool, that is Haar wavelet transformation. So the corresponding vectors are the scaling and the wavelet vector here. So this computation will lead to these sets here at the three stages, and here it is the input you see on the left hand side here. So here we see an equally efficient inverse transformation also possible for the reconstruction of the original samples into the signal f of x, and that is of course with the help of dwt oblique the efficient implementation fwt, that is approximation and the detail coefficients here, or you can say the scaling and the wavelet coefficients here, correspondingly denoted by w suffix phi and w suffix psi in the bracket j minus k. They can also be formulated here. So this is nothing but the inverse type of the fast wavelet transformation. We can denote it as fwt to the power minus 1, or in general way also ifwt is also one of the notation here. So this will use the scaling and wavelet vectors that will be employed in the forward transformation together with the label j approximation and the detail coefficients to generate the label j plus 1 approximation coefficients here. Now you see for the inverse filter bank, it is not that of the analysis type, but it will be of the synthesis type. You see here the multipaths are now joining to give a composite representation here. So this is what the wavelet function here, the w suffix psi in the bracket j comma n, and the another one for the scaling case w suffix phi in the bracket j comma n here. So these are for the synthesis type, not by the downsamplers but by the interpolators here. The upsampling is carried along with these two filter functions here. Further, the summation is giving us the representation of w suffix phi as a function of j plus 1 comma n here. So this was the information for the inverse transformation here. So as we see the perfect reconstruction of the two band orthonormal functions here that require the relation g suffix I of n is equal to h suffix I of minus n for the I value opting between 0 to 1. That is, the synthesis and analysis filters must be time reversed versions of one another here. So this is what the information we have shared a lot for the wavelet transformation here. Basically we have opted the one dimensional case here. So the modification from the one dimensional case, we can go up to the two dimensional also. I will like to conclude this in brief here, where we can say that the possible case is to also use the bi-orthogonal analysis and the synthesis filter, which are not at all the time reverse versions of one another here. The bi-orthogonal analysis and synthesis filters, if you work with, they are basically the cross modulated versions. The inverse of the fast wavelet transformation. So if it is used, the corresponding filter bank we will definitely show you. So it is also of the synthesis type, and the relation mathematical here we have the w suffix phi of j plus 1 comma k is equal to the convolution between the function h of phi as a function of k with that of the upsampled version of the wavelet coefficients here, and the another term is also having the convolution operation with that of the function of the wavelet time, provided that the k is always greater than or equal to 0. So w suffix up signifies the upsampling. Here the upsampling is by the factor 2 here, so the number of samples will be doubled here, and mostly this is made possible by adding of the zeros here. Now the upsampled coefficients are filtered by the convolution with h suffix phi of n and h suffix psi of n and further added to generate a high scale approximation, and in essence a better approximation of f of x with greater details and the resolution is further created here. So now you visualize the synthesis filter bank for this inverse transformation, and here we utilize a two stage, also known by a two stage synthesis filter bank here. So here you see the corresponding representations leading to a composite representation on the right hand side here. So this coefficient combining process is there from left hand side to right hand side that can be extended to any number of the scales. Here it is, for example, only the two scales here. In the beginning example we have talked about the three scale, and that it was of course for the forward transformation leading to the analysis type here. For inverse transformation here it is the synthesis type here. So for the one dimensional fast wavelet transformation, one of the example we have dealt in the previous slides here. For the inverse case also we can also represent it on the block schematic here for the two scale or the two stage inverse fast wavelet transformation synthesis filter bank here, and you see here on the right hand side from the coefficients those were initially fed as input to these various paths here, we have obtained fn that is recovered with the coefficient values 1 comma 4 comma minus 3 comma 0 here. So the formation of the same here it is discussed, and that is made possible on the right hand side here. Now we can note several differences between the forward fast wavelet transformation and that of the forward fast Fourier transformation. I will like to point out for the first time the number of mathematical operations involved in the computation of the fast wavelet transform of the length m is equal to 2j sequence is on the order of O in the bracket m here. That is the number of floating point multiplications and additions using the filter banks is linear with respect to the length of the sequence, whereas the FFT algorithm requires O in the bracket m log m here. So this is the one very important point here. The second point is with respect to the basis functions. For the Fourier type, the basis functions are of the sinusoidal shape that guarantee the existence of the fast Fourier transformation, whereas the existence of the fast wavelet transformation depends upon the availability of the scaling function for the wavelets being utilized, as well as the orthogonality or the bi-orthogonality of the scaling function and the corresponding wavelets here. So for example, there are various types of the wavelets in the family here. It's a big family. If you take the Mexican hat wavelet that does not have a companion scaling function, that cannot be used in the computation of the fast wavelet transformation here. So here the time and frequency are usually used as the different domains when representing the functions, and they are inextricably linked here. And if you want to precise the information about time, you must put up with some vagueness about the frequency, and then you can set a trade-off here. So this is what the unwanted Heisenberg uncertainty principle that is applied to the information processing here. The same can be illustrated here with the help of the figure. Here you see the time frequency slicing. We have A, B, C parts here on the left extreme. You see the sampled data, frequency on vertical axis, time on the horizontal axis. Then the application of the FT will give us the information on the frequency scale only, not on the time here. Whereas with the help of the fast wavelet transformation basis functions here on the left hand side in the part C, you see here the details are there available at the frequency scaling as well as the time scaling here. So these are the additional points that just now we have visualized here with the help of the delta function, the representation and all it is said here. So I think enough information I have shared with you people. Because of the time limitation I will stop here, and if you want the added information how exactly the wavelet transformation work on to the signals of the two dimensions, that it is the image, you sure attend my videos. Those are already available online here, or you can also ask me the doubts in my live sessions here. So thank you.